Good morning. We're going to start our next unit over the periodic table. So this lecture is going to be about the history of the periodic table and basic atomic structure theory. We're going to move into periodic trends and how the periodic table helps scientists understand how their elements or their molecules or even their chemicals are going to react based on the information that's provided for us in the periodic table. So we're going to talk about first is how they are organized. So periodic table is called a periodic table because it is periodic. It's organized by periods. Within these periods, you have things based on reactivity, the states of matter that these elements make up, whether they're soluble or not, their ability to conduct electricity. Those are just some of the properties that led to the organization of our current periodic table, our modern periodic table. So John Newlands was the first to notice what's called a periodic pattern. He arranged them in 1865 according to their increasing atomic mass. As he studied this arrangement and he noticed that all the elements in a given row had similar chemical and physical properties, this led to what's called the law or the rule of the octaves. So every element on the periodic table wants to have 8 valence electrons, and we're going to get to that here in a few slides. The next person to come along was Dmitri Mendeleev. So he invented the first periodic table. This was in 1869. He used Newland's observation, and he produced the first periodic table of all 63 known elements. So there were only 63 known elements in 1869. Today there's around 116 to 18, depending on which periodic table you look at. But every time a pattern repeated, Mendeleev started a new row. So two interesting observations about Mendeleev's table is it contained gaps that elements with particular properties should fill, and that the elements didn't always fit together neatly. So think about iodine and beryllium. And if you look at iodine, iodine is actually weighs less than beryllium, which was right before it. So it's one of the exceptions. So periodic law states that when elements are arranged according to their atomic number, elements with similar properties appear at regular intervals. This was the work of Newlands, Mendeleev, and Moseley all put together. So the periodic table is one of the great scientific collaborations. If it wasn't for the work of these 3 individuals, it'd be very confused on what to do with it now. So the organization of our current periodic table, it is based on electron configurations. Elements in each column have the same number of electrons in their outer energy level. These are called valence electrons. So if you look at group 1, which starts with hydrogen and ends with francium, those have 1 valence electron. Group 2 has 2 valence electrons. And you're going to skip the transition metals, groups 3 through 12. The group numbers that I'm saying are at the top of the periodic table. So group 13 starts with boron. It's the boron group. They have 3 valence electrons. The carbon group 14, has 4 valence electrons. Your nitrogen group, or group 16, has 6 valence electrons. Nitrogen group has 5 valence electrons. I misspoke. Oxygen group has 6 valence electrons. Your group number 17, those are called your halogens. They have 7 valence electrons. So you need to know that fluoride is the most electronegative element on the periodic table. It kind of tells everybody else what to do. Since they want to get to 8, and everything in that family has 7, or that group has 7, they get that 1 very easily. It's easy for fluorine to take on 1 more valence electron and become a -1 than it is for nitrogen to lose 5. So nitrogen would have to lose 5 to get to 8. Nitrogen, it's easier for it to gain 3. So they want to get to 8. They want to get to 8. And then finally, group 18 are your noble gases. Since they already have 8, they don't really react with a whole lot of other things. Okay. So a vertical column on the periodic table is called a group or a family. A horizontal row is called a period. Your horizontal rows are your energy levels. You've got 7 of them. 1, 2, 3, 4, 5, 6, and 7. Elements in the same period also have the same energy level. I just said that. All right. So period 2 is going to have 2 energy levels. Period 6, which starts with cesium, is going to have 6 energy levels. This is the outermost energy level. They have more, but they have at 6. So law of conservation of mass, you've learned this in biology, or you should learn this in biology. So a man named Lavoisier said that mass is neither created nor destroyed. It just changes form. So in biology, we talked about the tropic levels, and only 10% of the available energy carries through to each tropic level. So that energy isn't created nor destroyed, it just changes its form. So all those calories that you eat throughout the day, they provide heat, they provide nutrients, they help humans keep our 98.6 degrees at all times. So our total mass of our reactants is always going to equal the total mass of our products. Dalton in 1808 came up with his postulates or his atomic theory, and he stated that, let's cover up Dalton right here. He said that all matter is composed of extremely small particles called atoms. He said that atoms of a given element are identical in size, mass, and other properties, and atoms of different elements differ. Okay. He also said that atoms cannot be subdivided, created, nor destroyed. So that kind of goes along with what Lavoisier said with conservation of mass or matter or heat or whatever word you want to substitute there. And he also said that atoms of different elements combine in simple whole number ratios to form what's called a chemical compound. In chemical reactions, atoms combined, they're separated or rearranged. So modern theory has had several changes, but not a whole lot. So Dalton said that atoms of a given element are identical. So our modern atomic theory states that atoms of an element have a characteristic average mass, which is unique to that element. So if you look at the atomic mass of, if you're looking at carbon's atomic mass that's on the periodic table is 12.01. You could put another 1 at the end if you wanted to, but that's its average weight of all of the atoms that exist of carbon in the world. Number 2, he said that atoms cannot be subdivided, created, nor destroyed. Our modern theory, because of technology and advancements, and the more we know about science, the more we can improve on it, says that atoms cannot be created nor destroyed in ordinary chemical reactions. So if we're talking about a nuclear reaction, this can happen in a nuclear reaction, but they didn't know about this when Dalton's theory came out. So J.J. Thomson used a cathode tube to discover the electron. Electrons are your negatively charged particles. They float around the nucleus of the atom. They are not actually in the atom. So this is kind of what he did. We're not going to spend a whole lot of time on it. Just know that Thomson gets credit for the electron, and electrons are negatively charged. We're going to skip Thomson. Millikan determined that the charge of an electron was -1. He used an oil drop apparatus in 1909. I'm going to skip all of that. So Rutherford did what's called a gold foil experiment. So his alpha particles were helium. Particles fired at a thin sheet of gold foil. The particles hit on a detecting screen, and then he recorded the images. So Rutherford gets credit for discovering what's called the nucleus of the atom. So within the nucleus of an element, you have protons, which are positively charged. You have neutrons, which have no charge. They're neutral. So neutrons are neutral, protons are positive, and electrons are negative. So he found that most of the particles he fired went right through. A few particles were deflected. Very few were greatly deflected. So he said the nucleus was small, it's very dense, and it's positively charged. Well, of course, because it's only got protons and neutrons. James Chadwick was credited for discovering the neutron. It's a component of the atom's nucleus. It has no charge. They're in a nucleus to add mass, which adds to the stability of the atom's core. So when we're looking at it again, electrons are negative, -1. They float in what's called the electron cloud around the nucleus. We've got protons that are +1. They're found in the nucleus, and neutrons, which are neutral, they have no charge, and they're also found in the nucleus. So when we're looking at atomic numbers, and we're trying to figure out whether it's the atomic number or the mass number, we're going to have all this information is going to be available to us on the periodic table. So we take carbon. The 6 above carbon means that's the number of protons, which is also its atomic number. So the number of protons is automatically the atom's atomic number. Phosphorus has 15 protons. Its atomic number is 15. Gold is 79. Its atomic number is also 79. So the atomic number is the number of protons in the nucleus of an atom. So if you got a periodic table symbol, you're going to have it like this. So we're going to take helium. Helium, the elemental symbol is He. Its atomic number is 2. So that means it's the number of protons. That 4 on the bottom. So if we wanted to figure out how many neutrons were in the nucleus, we would take 4, we would subtract 2, and we would get 2 neutrons. We're going to round the numbers because you can have 0.003 neutrons. Again, this is an average mass, so that's why it has a decimal number. So this 4.003 is the mass number, or the atomic mass. For our work in our class, we're not going to round these. We're just going to leave them like that. We will round some. Oxygen 15.99, let's just use 16. Carbon 12.01, so let's just use 12. But to get you in the habit of writing them, let's just write them like this. So yeah, atomic number is 2. Number of protons is 2. Helium is going to have 2 neutrons because I did 4 minus 2. And its atomic mass is 4.003. So when we look at oxygen, if we look at oxygen on the periodic table, it has an 8 on the top and it has a 15.99 on the bottom. So that 8 on the top is going to be our number of protons. So since neutrons is 10, standard would be 8, but this is an isotope. So it's going to have 8 electrons, and its mass is going to be 18. So the reason that protons and electrons are the same number, unless it has a charge to denote it, or it's what's called an ion, elements are neutral. They don't have a charge on the periodic table. So unless you're given a unique symbol, and I'll show that to you in class, just assume that protons is going to equal electrons, because electrons and protons have to balance out. Your positives and your minus charges have to be the same for it to be an element with no charge. So arsenic on the periodic table, its number of protons is 33. So the number of electrons is also going to be 33. And we're going to take 33 plus 42 gives us 75, which is going to be our mass number, which we're going to put right there. Same thing for phosphorus. Phosphorus is element number 15. So number of protons is 15. Number of electrons is also going to be 15. Since my mass number is 31, I do 31 minus 15, and I get 16. Isotopes occur in nature as, elements occur in nature as a mixture of what's called isotopes. So isotopes are the same element, but they just have a different number of neutrons within their nucleus. So their mass is going to be a little bit different. They're always going to have the same number of protons, because if you change the number of protons, you change your element. So they're going to say number of protons, different neutrons. For example, you can have hydrogen. You can have hydrogen 1 or you can have hydrogen 2. You can have helium 3, helium 4. You can have lithium 6, lithium 7. We're just adding neutrons. We're going to keep the same number of protons. So that average atomic mass, we're going to do a whole separate lecture over how you calculate average atomic mass. But this is why carbon is 12.011 instead of just a nice number 12, because 98.89% of all carbon in the world is carbon 12. 1.1% is carbon 13, and less than 0.10% is carbon 14. We're going to figure out how to calculate this at a later date. If you have any questions when you're working on your work, just let me know, and I will be available to help. Have a great day.